All right, today what we're going to look at is when we deal with rotating objects in energy. Okay? So if an object's moving linearly, we use kinetic energy as 1/2 mv squared. If it's rotating, we talk about 1/2 I omega squared, where I is the moment of inertia about the axis of rotation of our object. So when I talk about kinetic energy from here on out, it's going to have two parts. It's going to have a part for something that's moving and a part for something that's rotating. Now, if it's just moving, we don't have this part like we did before. Or if I have just an object that's purely rotating, it's not actually going anywhere, I only have this part. But if it's both moving and rotating, an example of this would be rolling, I'm going to include both parts of the kinetic energy. Okay? Now, there is a link between this linear kinetic energy and this rotational kinetic energy, and it has to do with that if an object is rolling without slipping, now without slipping, that means that the velocity of the center of mass of the object is equal to the angular velocity times the radius of the object. And we're going to use this when we do problems for rolling objects. So let's try one. So the example problem states that I have a basketball that's going to roll down an incline, and the incline is 2.2 meters high. The mass of the basketball is 0.625 kilograms, and its radius is 0.12 meters. And we want to know how fast is it going down here at the end. Okay. Well, it's a basketball. So which of my moments of inertia on my table best represent a basketball? I would say a thin-walled, hollow sphere. And so my I comes out to be 2/3 mr squared. All right. So this is a work kinetic energy problem. We have a starting point at the top. We have an ending point at the bottom. Okay. So we're going to ask ourselves some questions and cross some stuff out. So work in. Is there anyone pushing the basketball as it goes from point 1 to point 2? The answer is no. Is there any friction? Now, you'd say, well, if there was no friction, guess what? It wouldn't roll. But there is friction, so it is rolling. But when we talk about work done by friction, we're going to talk about that friction pulling energy out of the system. So think about something sliding. Don't think about something causing rotation. Because all friction is doing is it's transferring some of that energy into rotation. So there's no work done by friction because it's not sliding. Okay. Is it moving at the bottom? Yes, and it's both has a velocity and a rotation. And so we're going to have both parts of the kinetic energy at the bottom because the ball is rolling. At the top, it hasn't started moving yet. At the bottom, the height is 0. At the top, the height is 2.2 meters, and there are no springs involved. Okay. So let's start making some substitutions. So I have kinetic energy at the bottom, and because the ball is both moving, 1/2 mv squared, and rotating, I'm going to have both of those kinetic energies involved. This is all of K2. Okay. Minus UG1, which is mgh. Okay. Now, if you look, we don't have a mass in all our terms. But if we're kind of clever here, and so if we have an object that's rolling without slipping, we can use this substitution that VCM is equal to omega times R, or I could say that omega is VCM divided by R. So that's what we're going to do. We're going to do a lot of substituting in this space. Okay, and you're going to see why in a second. So I have 0 is equal to 1/2 mv squared plus 1/2 times I. For our hollow sphere, it's 2/3 mr squared. And for omega, because it's rolling, omega is going to be velocity divided by the radius of the object. Quantity squared minus mgh. And when we make these substitutions, we're going to start to see things like, now I do have a mass in all three terms. I also have an r squared and an r squared that cancels out. And so what I'm left with here is I'm left with 1/2 v squared plus 1/2 of 2/3 is 1/3 v squared. Oops. Minus gh. And I'm going to try and solve for v. So a half plus a third is 5/6. So I have 5/6 v squared equals gh. And just continue on solving for v, and I get v is equal to 6 gh divided by 5 square root. And you can plug that in and get an answer. Then you'll have, it looks like, a couple clicker questions to try, and then a practice problem. At the start of the next video, I'll give you a little hint on how to do that practice problem, and then we'll go on to the example number 19 as well. Okay.